Hello everyone, my name is Minuk Ma. Today I'm going to talk about DeepRL Bootcamp Lecture 5 about TRPO and PPO. This is the outline. TRPO refers to Trust Region Policy Optimization, and PPO means Proximal Policy Optimization. There are two limitations of vanilla policy gradient that we covered in last lectures. One is it's hard to choose the step size, and the second is its low sample efficiency. So first, it's hard to choose a step size. The input data in reinforcement learning is non-stationary due to changing policy. Observation and reward distributions change over time because we are updating the policy over time, so the policy itself changes, and we collect data through this policy, so our input distribution changes over time. Bad step is more damaging than in supervised learning, since it affects visitation distribution. So simply saying, let's assume that the step size was too large, so we stepped too far, then we'll get a bad policy. Then in the next batch, we'll collect data according to the bad policy. Then we may not be able to recover from that, and the performance will collapse. The second drawback is low sample efficiency. So unlike in DQN, which enjoys experience replay, which allows the system to access to previous experiences or previous data, policy gradient algorithms use the data only once for gradient step update and then discard it away. So we cannot say that policy gradient algorithms use data efficiently. So we're going to introduce surrogate loss and then TRPO, which can resolve these two issues. So the policy gradient algorithms use this kind of quantity called policy gradient, which is the expectation of differentiation of log pi advantage. This here advantage can be like reward or Q minus V, something like that, as we discovered in last lectures. So how can we get this quantity? We can differentiate the following loss, but don't want to optimize it too far. So this LPG theta is defined in this way. If we differentiate this quantity with respect to say theta, we can get this policy gradient, right? Now equivalently, we can differentiate this loss function. They're exactly the same. Note that there was log function here, but now there's no log. We can derive this formula by simple mathematical trick. This is the outline for TRPO. As I said, TRPO stands for Trust Region Policy Optimization. There are 4 steps. First, I'm going to propose optimizing surrogate loss. Oh, I actually proposed already. The second, we're going to use KL divergence to constrain the size of update. Third, we'll find that it corresponds to natural policy gradient step F inverse G under linear quadratic approximation. Fourth, we can solve for this step approximately using conjugate gradient method. Since calculating this quantity, F inverse, is computationally expensive, we're going to use an approximate algorithm, which is called conjugate gradient method. Now it's TRPO. Let's define the following trust region update. So this is our surrogate update. We're going to maximize this under theta, subject to a constraint. So KL divergence of the old policy and the new policy should not be greater than, should be less than or equal to delta. So this basically means we want to maximize this quantity, but we don't want our policy to change too dramatically. We can also use other kind of distance measures like Euclidean distance in parameter space or whatever else, but probably this distance measure is the most intuitive measure because this deals with the policy distribution themselves. Also, it's worth considering using a penalty instead of a constraint. So basically this is a constraint optimization problem, and in many cases in machine learning, we convert this problem into an unconstrained problem using the Lagrange method, or the method of Lagrange multipliers. Simply saying, the optimality point of delta constraint problem is also an optimality point of beta penalized problem for some beta. Now, before we move on to the details of TRPO algorithm, let me explain one monotonic improvement result, one theoretical result. The theory says if we use max KL instead of mean KL in penalty, then we can get a lower bound on policy performance. I mean, if we use max here instead of mean, then we can get a lower bound, theoretically, on policy performance. So, in the figure below here, if A dot theta was the actual performance graph, then our surrogate loss function, the green line, only approximates the real performance line locally. But when the step size is too large, it deviates too much. So we want to subtract some terms called penalty from that L theta for ensuring safe update. This is the pseudocode for TRPO. For n iterations, we run policy t times steps or n trajectories and sample data and estimate the advantage function at all time steps. Then we can calculate this an hat, and we construct the surrogate loss and maximize this term under theta, subject to the constraint. We can solve this constraint optimization problem efficiently by using conjugate gradient. I'm going to explain it more in detail later. And it's closely related to natural policy gradients, or natural actor critic, and RAPS algorithms. Now let me explain how to solve the KL penalized problem. This was the optimization problem, maximize under theta of the surrogate loss minus beta KL. We make two assumptions. We make linear approximation to L and quadratic approximation to KL term. That is, this whole problem becomes this. So L term becomes this, and KL term becomes this, where G is policy gradient, namely the derivative of L with respect to theta, and the second derivative term here, where quadratic part of L is negligible to compare to KL term. F is positive semi-definite, and we'll find that the solution is this. Before in vanilla policy gradient, we only had this G term, but now we have this F inverse term and one scaling factor, 1 over beta, where F is called a Fisher information matrix and G is policy gradient. This analytic solution is called the natural policy gradient algorithm. This is, you can think of it like Taylor series like expansion. And note that this KL divergence term, it can be thought of as a second order distance metric because it is minimized when the two distributions are the same, and when they deviate either to the left or right, the KL divergence term will increase. So it looks like this. And if we differentiate this kind of function 2 times, f becomes positive semi-definite, which means all eigenvalue are 0 or positive, are non-negative. Why is it important? If f is positive semi-definite, then we can approximate calculating this f inverse using an algorithm called conjugate gradient algorithm. Because usually calculating this f or f inverse requires a lot of computation. So in trust region policy optimization, we usually use conjugate gradient to approximate this. We can calculate this term f inverse g without even constructing the f matrix itself. But let me skip the detail. Now, beta only affects scaling of solution, but not the direction. We computed S equals f inverse g when beta was 1. We're going to rescale theta minus theta old as alpha s so that the constraint is satisfied. So we want the KL divergence, we approximate it in this way, and we want it to be the same as delta. Then we set theta minus theta old as alpha s. So this is alpha s transpose fs. And if we solve this equation, we can get alpha equals this. Even better, we can do a line search to solve the original nonlinear problem without any approximation. So this is the original objective, and try many scaling factors until line search objective improves. Now let's move on to the actual implementation of TRPO. So in summary, we update parameter in this way. Theta old plus scaling factor f inverse g. Okay, so define TRPO. And first of all, there's one for loop for iteration, and then collect sample according to the current policy, sample trajectories to estimate the advantage function. The first main step is to compute G, the policy gradient term, as in vanilla policy gradient. Here is surrogate loss and surrogate loss dot backward. Then we can get the policy gradient. The second step is to compute the f inverse g using conjugate gradient algorithm. This is just compressed in this function cg, conjugate gradient. Then we can get the direction, what direction to go, but still we have to get the scaling factor. And we can calculate the scaling factor as in the previous formula I explained. Then we have direction and scale. Then we get the parameter update step. Then we can just plug into here to update the parameter. Let me explain the results. The pros of TRPO is that it's more stable learning than vanilla policy gradient or even natural policy gradient algorithm. It works good for control tasks like Cheetah, Hopper, Walker, then DQN. Cons are it's hard to use with architectures with multiple outputs, and it's empirically performed poorly on tasks requiring deep CNNs and RNNs, like in Atari benchmarks. But it's empirical, there's no theoretical analysis. And conjugate gradient algorithm makes implementation more complicated. Now finally, let me explain the demo results. This is OpenAI Gym Pendulum environment. There are two discrete actions, left and right. The goal is to make Pendulum upright with least effort. At 0 iteration, the agent doesn't work at all. And after 20 iteration, it sort of starts to work, but sometimes it fails. After 45 iteration, it almost works perfectly, but maybe not perfect.
The next topic I will present about the proximal policy optimization. The previous slide had been about the TRPO. There are some limitations of this algorithm. The first is the TRPO performs poorly on the task requiring deep CNN and RNN. The second is the solution of TRPO involving a second-order derivative matrix make implementation more complicated and not scalable for large-scale problems. So PPO propose new kind of loss called adaptive KL penalty coefficient and clip surrogate objective. The loss is using first-order optimized line gradient descent so that its computation is smaller. It is suitable for large-scale problems. Here I will talk about the adaptive KL penalty coefficient. The KL penalized loss is present as below. The first term is the importance sampling loss. The second term is KL divergence that measures the divergence between the policy theta O and new policy. The beta is a penalty coefficient. The coefficient beta will adaptive after several epochs. This lot makes the policy not change too much from away by theta O by adjust the beta suitable. Here is a pseudocode of the adaptive KL penalty coefficient. The input of the algorithm is initialized parameter of policy theta 0, the KL penalty beta, and the target KL divergence delta. For each iteration, we will run the policy by theta 0 in the environment for t-time step and correct the trajectory. After that, we will compute the advantage estimate A1 to AT. Then we do the stochastic gradient descent on this slot for some number of epochs. Then compute the KL divergence between the old policy and new policy. If the KL divergence is too high, the beta coefficient will increase. If the KL divergence too low, the coefficient is decreased. Here I will talk about the clip surrogate loss. This loss is better than adaptive KL penalty in the artery benchmark. First, let me recall the TRPO loss, or calling the importance sampling loss. It's computed by take the expectation of the probability ratio multiplied with the advantage estimator. Let's denote the probability ratio as the RT theta. This loss without the constraint, if we maximize the loss, can be exceed large probability update, then make the decrease performance. Then the clip surrogate loss is proposed to constrain the probability ratio not far away from 1. Here. Let me talk more detail in this loss. The first term inside of the mean is importance sampling loss. It is similar with the TRPO loss. The second term is clipping the probability ratio, which removes the moving of the RT outside of the interval 1 minus delta and 1 minus epsilon and 1 plus epsilon. Here is the clip surrogate loss pseudocode. The input of algorithm is the initialized parameter of policy theta O, the clipping threshold epsilon. For each iteration, we will do same as the adaptive KL penalty. First, we run the policy by theta O in the environment for t time step and then collect the trajectory. Then we will compute the advantage estimate A1 to AT. Then we do the stochastic gradient on the clipping loss for some number of epoch and update. Here is an example about the car pole. In the example, we will control a car by moving it to the right or left so that the preventing its joint from falling over. Here. Let me explain the problem more detail. After taking an action, we will receive an observation or state that includes 4 features. The first is the car position, the second is the car velocity, the third is the pole angle, and the last is the pole velocity. Here. The observation space is a continuous space. Here is the range of this feature. Here. The action includes put car to the left or put car to the right. The reward is the one for every step taken, including the termination step. The episode termination when the pole angle larger than 12 degrees or the car position larger than 2.4 units or the episode length larger than 200. Here is the implementation of this problem in the Python. Here is a loop for the number of iterations. The first, we will collect trajectory with a given policy by theta O, and then we will collect the sequence of the observation reward. Then we will compute the advantage estimator AT. This algorithm takes the input is the reward value, previous value, and previous next, and value of next. Then we will compute. We will train policy with the stochastic gradient on the clipping loss. Here is the conditioner to stop training. The stop conditioner will execute when we perform success larger than 100 rounds. Here is the result of the training. The x-axis is a number of iterations. The y-axis is the episode length. As we can see, in the early of the training, the length of the episode is too short, and then it's increasing after after few hundred number of iteration. After 600 iteration, there number of the episode that is reach the 200, the iteration, the 200 time step here. And here is the demo when the before training. The couple is terminated after 67 steps. And here is the result after the training. The couple stop after reach to 200 step. Here I complete my presentation.